All right, welcome back, everyone. As I promised in the first week, I am not, the goal of this class is not for me to talk at you the entire time. And today we're actually going to start with someone who's much better at explaining this topic than I am. I'd like to welcome Sergey Karayev. Sergey was an AI PhD at Berkeley, and then he started a company called Gradescope. Gradescope is sort of an automated grading platform, and I first encountered it when I was in my first semester at Berkeley teaching a 400-person calculus class, and Gradescope was kind of a lifesaver in that setting. Gradescope recently was sold to Turnitin, and Sergey is now the head of AI for STEM there. So he's going to be talking to you about some of the work they do more broadly, and then also some of the topic of the lecture that you watched on AI or on infrastructure. So welcome, Sergey.
Thank you. Thank you. So I'm actually going to start with a talk that is kind of new to me, but it's this concept that when you're building AI applications, or as an investor, people pitch you on whatever they want to build, or maybe as someone in a company, you're considering implementing something that someone has developed as a product. How do you actually know whether it's a good thing to build, fund, or deploy at your company? So since my background is in, I guess, the company I started is about grading, I thought a nice lens to look at it through would be a grading rubric. Like if you had to grade a potential AI application, what would you look for? What are the dimensions? So before I get into that, briefly about me, just going to move this, is currently I work on AI specifically for science, technology, engineering, math at Turnitin. Turnitin is a pretty big tech company, actually one of the largest. We have 35 million students under contract at over 150 countries. The way I got there, we're also based in Oakland, so we're neighbors. The way I got there was through co-founding a company called Gradescope. And Gradescope was, as Josh described, essentially software for grading kind of STEM work. Turnitin is software for grading and checking for plagiarism of writing work, so essays and stuff like that. So it was a natural kind of match for us to work together. We founded Gradescope in 2014, and we got acquired in the fall of 2018. So it's pretty recent to me to be at Turnitin. I'm also one of the co-organizers of Full Stack Deep Learning, which Josh also organized, and some of you I recognize from that, so thanks for coming. And then before that, I was a PhD at UC Berkeley. I was working in computer vision. I was working on using methods from reinforcement learning for computer vision tasks. And towards the end of my PhD, deep learning started kind of becoming a thing that you had to do. So we actually had a deep learning framework called Cafe that we developed in our lab. I'm one of the authors in that paper. It was a fun ride kind of in the last couple of years of my PhD to really see that take off and the community grow and Cafe become kind of the industrial de facto deep learning framework. Then I graduated and kind of shifted gears into education technology. So my goal for these slides here today, and I'll get to the infrastructure lecture after this, which I understand you've seen on your own time at home. So we'll just kind of do mostly Q&A for that. But my goal for this lecture right now is to get criteria for evaluating AI projects and applications, funding, deployment, development. And this will be with a particular focus on education, because I'm about to give these slides at a conference for the UN, which is kind of cool, specifically in the education track. It's called the UN AI for Good conference. So good PR. So the first thing that I want to convey to you guys is that it's early days for actually deploying AI in your product. So there was a 2018 survey of 300 people or more that actually worked on machine learning kind of as their job, from all kinds of industries, from education to fintech to developer tools, all kinds of stuff. And one of the questions was, what phase are your AI projects today, right? And so production rollout is a small minority of what people are actually doing with AI. Most people are still in the feasibility study or the architecture planning or the kind of application development phase. So I think, we shouldn't feel bad that we're not all deploying AI to production if we're not. And we should feel good about the opportunity that's there because it's very greenfield still. But when you start working on it, you should consider certain criteria when you decide what to work on. And the categories I want to suggest are, one, task formulation. And the kind of the grading rubrics will be an X, which means like you're doing a bad job, a check minus, which is better but not perfect, and then a check plus, which would be like, that's kind of where you want to be. User interface / performance requirements, the difficulty of the technical problem, the data mode that you initially start with, and then the flywheel that you can get spinning as your product is actually shipped. How does data kind of help your product become better? So to start with, we can do task formulation. And what I mean by that is really, is the problem well-defined? Can you formulate metrics for it that people can agree on, that are clear to everyone, and that you can measure? This is really the foundation of the whole project. You're not supposed to build a house on sand. So if you build your whole AI application on a premise that's flawed, then what are you doing? So I think the worst thing you can do is develop AI, or if someone's pitching you as an investor or a potential employee at a startup, they're selling AI as just a magical solution to a problem that hasn't been solved in any way and is kind of hard to measure or potentially unmeasurable. So what I could give as an example is like, I'm working on AI for achieving human happiness, right? Like, I have many questions about that. How do you achieve happiness without AI? We don't really know. We can't even agree on a definition of happiness. How are you going to measure progress on it? What is the AI supposed to do? So I would give this 0 marks. What's that? AI, yeah, build AI, question mark, profit. A better task formulation is a task that's complicated. So it's not very clear how it should be done. It's complicated, and people have trouble doing it. But we do know that some people can do it, and it's possible for us to agree that someone's doing a good job or not on it. And here, I think it's very important to have experts, like subject matter experts in this particular task, involved from day zero, like designing the product, thinking how it should be deployed, what data you need. And so an example that I can give from kind of my current company is giving students feedback on their writing, right? So a student submits a piece of writing to a specific topic, and then what they can get from it is high-dimensional kind of feedback, high-quality, high-dimensional feedback on 4 dimensions. So how developed are your ideas? How organized are your thoughts in support of those ideas? How clear is the language that you're using? And then the mechanics of the language, like are you making grammatical mistakes and such. And this task is definitely hard, right? And in human world, you tend to go and get a master's to be able to do it. But we can agree that some people are better than others at it, and we can agree that you can do a good job on it. So if someone gives me an essay and I just scribble randomly on it and hand it back to them, that's bad feedback. But if I actually take the time to read it, I highlight certain things, someone else reads it and they would agree with what I say, that's good feedback. So can we replicate that? And an even better formulation of a task is something that's so well defined, and there's potentially even a good baseline solution for it that doesn't really use much AI. That could be just, you can hire anyone in the world, any one of 6 billion people to do it for a cent. That would be a good baseline to start with. And so an example could be Facebook face recognition, right? So we can all agree, is this the same person or not? It's a binary kind of prediction that you're making, like it is this person or not. And so this would be like a really clear task formulation. The next thing you should think about is user interface / performance requirements. The first question is the AI entirely autonomous, or is its goal to assist the user? This is, sometimes this is called AI versus IA, like artificial intelligence is kind of off by itself, and IA is intelligence augmentation. So this is like human intelligence, but augmented by a computer. And we call this like autonomous or assistance. What percentage of the time does the AI need to make a prediction at all? And if it makes a prediction and the prediction is mistaken, how bad is that for the situation? So this is a slide from Josh. The reason this is kind of important is because if you want to get to really good performance, that might be 10x or 100x as difficult as getting to like a decent level of performance. So the worst marks are for a situation where AI has to be 100% autonomous, has to predict all the time, and if it makes any mistake, people die. And an example of that is a self-driving car, right? It's like that's the purpose of it, is to be self-driving, so you're not involved at all. But if it screws up, then you personally might die. So the reason it gets low marks, obviously, it's a very enticing application to work on, and the reward is very great, but the risk is also very great. It's a difficult problem. What's a little bit better for you to consider working on is something where, sure, the AI has to make a prediction for every input, but it's not so bad when it makes a mistake, and the user actually can correct the mistake, but maybe they're annoyed by it. So an example could be a speech-to-text transcription on my phone, right? I use it often. It's useful enough for me, but oftentimes, almost every time, it makes some kind of mistake. And so here, it's very important to think about the UX of the product and build in kind of nice user interfaces for the user to be able to correct the mistakes. So here, like the last word, I was trying to say trying out, but it, for some reason, perceived it as China, but it gave me a little button that I could just press and in one click correct it. What's even better is a situation where the AI doesn't even have to predict every time, so it's just kind of assisting you, not automating something. And actually, maybe the user doesn't even mind correcting the mistake so much. And I like to think that that's where we sit at Gradescope. So what we do is we assist the instructor in grading student answers, but we don't actually grade the answers for the instructor. What we do is we group the answers by content, and then the instructor can decide how to grade them. So let's say you have all these answers to a given question. They go through kind of our machine learning processing, and we spit out groups. The user, and we built a really nice interface for the user to correct the groups. So if we made a mistake, they can correct the groups. They can merge groups. They can delete groups. They also have to go through all of the groups to confirm that the answers actually belong in them. And then they decide how to grade the resulting group. And the best part of this is the instructors love it because it saves them a lot of time. Like, even though it's not perfect, let's say we grouped 80% of the answers, we still save them like 4/5 of the time that they would have spent. And so it was important to us to find a way to start introducing AI into our product that was like this, where like the AI didn't have to be perfect, but the user still found value in it. So for education applications specifically, if you kind of think of like performance requirements, so this could be like accuracy requirements, going from lower to higher. If you're aiding the instructor, the performance requirements is lower because the instructor is an expert. So you can kind of save them some time, but they still take responsibility for the final decisions. If you're aiding the student directly, then that's a higher bar to clear because they don't necessarily know when the AI is making a mistake or not. Because by definition, they're trying to learn something. If you're trying to like tell them something that's wrong, they might learn something that's wrong that could be very harmful. And the most harmful yet is actually replacing the instructor. So if you start grading student work instead of a human, then you better be 100% correct because someone might not get a scholarship or get into college or something like that because your AI is not perfect. The third dimension is technical difficulty. And so what I mean by this is like, what do you actually need kind of technically to solve the problem that you want to solve? And you look at analogous solutions, whether products or open source, look at the research papers that have been published, and talk to experts. And the worst place you could be is, the problem that you want to solve is like not just one, but several steps away from what you see working today or what you've seen working in research. And this will require like a world-class research team and just kind of an uncertain timeline. So an example in education would be a tutor that can tutor students in all subjects at all grade levels. We don't really have that for a single subject or for a single grade level, so that's several steps removed from where we are today. What's better is like you have reason to believe the problem is solvable, but you haven't seen it working in production just yet. So this will require a research team because it'll require adopting a known solution to kind of an unknown domain. And you might not actually get it working, but it'll at least have a shot. And an example I could come up with is like a robot that can teach infants a second language, right? So oftentimes people get a caretaker that speaks a second language to a baby because babies are really good at picking up language. We have little cute robots. We have Google Translate. We have, it feels like we have the right technology. We just have to kind of put it together and address this new domain. And probably what's easiest is like you've seen clear analogs that work, but it's not yet mainstream. So there's still a barrier to entry, but at least you're certain that you'll succeed. And so this doesn't actually need researchers, I feel. I think it just needs good engineers, and you can kind of put a time bound on it. So an example could be like you've seen that you can recognize handwriting, and math is like a special type of handwriting. It's more difficult because it's like two-dimensional instead of, it's not just down a line, it's also like fractions and stuff like that. But it seems like it's basically the same problem, but it hasn't been done until just a couple of years ago. So that's a great problem. When you start working on something, a very good thing to consider is like what data are you going to use initially? And the reason for that is like when you're working on defensible AI company or product, that usually means you're assembling a defensible data set, some proprietary data that no one else can get, or at least will have trouble getting. And this is why we see TensorFlow and PyTorch and a bunch of research come out of Google and Facebook and Uber and stuff like that, because the data is the actual thing that they hold proprietary. The methods are not. So for you, you should look at, is the raw data that you need available? How expensive would it be to label the data once you have the raw? And then could someone else come along and get it? So the worst part to be in is, the data is super expensive to obtain or label or both. But when you're done, someone else can just come and do the same thing. So an example could be satellite data. Like anyone can just buy terabytes of satellite data, pay the millions of dollars to label it, and now you're playing the same game. What could be better is if you get something that is expensive to label and difficult to obtain, but once you do, there's some kind of exclusivity. So like DeepMind, I think, partnered with the National Health Services in the UK recently to do like DeepMind Health or something like that. And so the data they got is for like the entirety of the UK. No one else could get it because it's an exclusive partnership. And it'll be an expensive project, but by the time they're done, at least no one else can kind of unseat them. And best yet, the data is exclusive to your company, and you already have it labeled. So for example, the nation of Singapore has detailed educational records for every citizen from kindergarten up until they enter college. No one else has it. No one else can get it. And it's already kind of labeled, like all the grades, all the demographic information. So that would be a great data set to start working on. Once you build your initial application, you should consider how you're going to handle new predictions, right? Are you going to monitor the predictions you're making on data you've never seen before? Will you be able to correct predictions that you make wrongly? And will you be able to easily retrain your whole system with the corrections? And best of all, could you just have your users do that for you? So 0 marks is for predictions not being monitored and not being corrected. And I'd say, as an example, most AI products, this would be this situation. And you're really kind of flying blind, right? So you train your first model, and then you start serving up predictions in your production environment, but you don't actually ever look at what's happening. So maybe at some point, the data format that your users are sending you changes a little bit, and your predictions are all wrong. Most companies wouldn't actually even notice that, and certainly wouldn't retrain kind of on a regular basis. What would be better is if you monitored your predictions, and then potentially the low confidence ones, so the ones your models wasn't certain about, went through a manual QA process with a team of annotators. And if you do that, then, if you do that, then you can get this kind of data flywheel starting to spin. And the idea is that when you first build your model, let's say you trained on like 1 million examples, right? And then that's enough to get something that's 80% accurate, so you ship it. And now your users are using it, and they're sending you 1 million of examples a month. So you could be doubling the size of your data set every month or so, right? And so the more users you have, the more data you have. So now when you have 2 million examples, maybe you're at 85% accuracy. Now all of a sudden your product is even better than it used to be. And so more users come on board and they give you more data. And so you kind of keep doubling that. And that's the idea of the data flywheel. Now, sending predictions through a manual QA process is great. It's better than not doing that, but it's very expensive. And the kind of highest marks here are for monitoring your predictions for like data skew and stuff like that, but then also letting your users actually let you know how to improve the predictions you're making. So an example I like to give here is Google Photos, where Google trained something on a fixed data set, but then they released it, and then they keep asking their users, are these two faces the same when they're not certain? And I don't know about you guys, but I always answer these questions because I actually don't want people's faces I don't want a stranger's face when I'm looking at my friend's kind of photo album. And also I do want my friend's face in my friend's photo album, so I'll answer yes and no. And that's very useful data for Google. Here's another thing that Google Photos does. I guess like the thing to convey here is this takes design thinking, right? So if you've already built your whole product and then you trained your AI and now you want to like get the flywheel going, it's probably too late at that point. You should have thought about how to build the product in such a way that you build in the hooks for the user to give you good data. And Google Photos, I think, is a great example of it, both with this user interface, but also with this other thing, which is search by content. So if I search my photo collection for dogs, I do get a bunch of images of dogs. That's great. If I search my photo collection for cats, I get some cats, but then I also get some dogs, right? These things are dogs. So Google Photos made a mistake here. And maybe I find it annoying. I'm a little OCD. So I'll actually find the user interface hook that they have, which is you click on the sandwich menu, and it shows a little thing that says you can edit date and time, you can download the photos, or you can remove the results. So when I click remove the results, I'm letting Google know that these things are not cats. They don't know they're dogs, but at least they know they're not cats. And they can infer that all the other photos I didn't click on actually are cats. And so very rapidly, they can improve the size of their content data set also. So I have a little transition here, which is, you got the cats and the not cats. Now that's going to feed into the machine learning model. But the machine learning model is just kind of a part of the overall code base that we're developing. And there's a lot of stuff around it. This is the figure from the paper, Hidden Technical Debt, or machine learning, the high interest credit card of technical debt. So the machine learning code, the cool neural network is just a part of the code base, but then you got all the stuff around it, right? And it actually requires many roles to do these tasks. So in a big org, when you're actually splitting up the roles instead of just hiring one person or doing it all yourself, you got data engineers, you got machine learning researchers thinking about what features, what architecture to do. You got machine learning engineers thinking about how to productize it, how to distribute training onto multiple GPUs or distribute feature extraction onto multiple machines in a cluster, how to monitor your running model, how to analyze, maybe reduce the size of the model once you trained it. And you got DevOps people providing the GPUs for you and then being responsible for the model serving up predictions at a reasonable speed. And so all of that is infrastructure and tooling. So how am I doing on time? So when should I end? I kind of don't know.
We had you for until 7:15, but if you want to go a couple minutes over.
OK. So here, I assume you guys kind of watched the lecture at home, the infrastructure and tooling lecture. I think there's really not too much I want to cover. I think maybe just as a review, I'll kind of rebuild this, this slide. And then I will highlight a few slides that I recently changed because some companies went out of business and some new tools kind of became mature enough to include here. And then I'll just take questions. So I think this will just take 5 minutes. But I break down infrastructure and tooling into kind of 3 sections. So you got data, development, training, evaluation, and deployment. So data, there's a whole lecture about that, but this is kind of also the infrastructure and the tooling that you need. This is kind of the contents of the infrastructure and tooling lecture. software engineering, machine learning frameworks, how do you manage resources, how do you do experiment management, how do you do distributed training, how do you maybe do like kind of smarter model training, hyperparameter optimization. On the deployment side, how do you do continuous integration, continuous delivery, how do you specifically deploy to the web, monitor your predictions, maybe get them working on embedded systems or on mobile. And then all-in-one is this trend of like Google, Facebook, Uber, Amazon, and then a bunch of startups noticing that all these things are kind of have to be done together in a certain sequence, and everyone's kind of figuring out the parts of that sequence for themselves. So could we just get like a best of breed all-in-one solution? So this is the infrastructure and tooling lecture content here. The things I want to highlight that recently changed are, maybe I'll just kind of quickly go through it, if that's cool. Like I'm not going to read the slides, but I'll just click through the slides. Software engineering, frameworks. Yeah, so the idea here is frameworks are converging on something that's both defined by run, so you can just write code and then run it, and then it figures out the graph automatically, and able to have a nice optimized graph. So both TensorFlow 2.0 and PyTorch 1.0 are like both of those. So people have a good time with PyTorch, but TensorFlow is just as good. TensorFlow is likelier to get you a job. I make a distinction between like just developing on your own machine or just on a desktop machine with a couple of GPUs where you can actually like open up images easily, just use your code editor that you're most familiar with, maybe use like a GUI for other tasks, and then also being able to train at scale. So that's kind of like the development, training, and evaluation phases. And the infrastructure needs might be different for those. So to get those, we cover GPU basics. Just going to click through this. Yeah, basically 2080 Ti's are like the sweet spot right now. This is what I recommend getting. Yeah, so a couple of machines are 1080 Ti's, and a couple of machines are 2080 Ti's, and then a Titan RTX for like big NLP models that don't fit into the 11 gigs of memory that the 2080 Ti gives you. And then another team uses cloud GPUs, but I still prefer on-prem GPUs because it's just so much more cost effective. And especially for these like 24 gig GPUs, it's just crazy expensive in the cloud.
Can you literally build them yourself?
No. So yeah, the choices you have are for on-prem options. You can build it yourself, which I think everyone should do if you haven't done it ever in your life, because it's just it's a cool experience, and you get hacker cred for doing it, and it's actually not that hard, and you get to save a couple of grand if it's like your own money. It's actually meaningful, and up to 4 GPUs is nice and easy. Going beyond 4 GPUs, you need like server rack mounts and stuff, and you don't want to do that. Or you can buy pre-built, and the two choices there are NVIDIA, if you want to satisfy their end-user license agreement, or Lambda Labs, if you don't care about the NVIDIA end-user license agreement. And it's actually not a 75% premium. It's only a 25% premium. I should have changed this. Over building the same machine yourself. So we've done that now also, and this is a good solution that I would recommend, Lambda Labs. And they might be willing to give you guys a discount, because we know the founder, right? I don't know. We'll have to ask him.
I tried to give a discount. You wouldn't give me a discount.
Oh, really? Dang it. So anyway, if you analyze the costs, it's like much better to build your own machine than to be in the cloud. So they use the 2080 Ti's and the Titan RTXs also. So you got 2080 Ti, and you got the Titan RTX.
And are they NVIDIA GPUs?
These are NVIDIA GPUs, yeah. And then I think they still have the 1080 Ti machines, but I'm not sure.
How much does it cost to build yourself?
If you want to build a machine with 2080 Ti's yourself, it would be like $7,000. If you buy it from Lambda Labs, it would be like $9,000. Kind of depends on exactly what GPU you want.
That's for 2, right?
I think that's for 2. That's right. Yeah. So anyway, if you like run the math on, if I built this machine and then ran it for like 4 months, that would pay for itself in terms of paying for an equivalent amount of compute in the cloud. So if you expect to do more than like 4 months roughly of compute, you should build it yourself. If you expect to do less, then I don't think you should expect to do any less. But then maybe the cloud could make sense. Or if you just want to run 100 experiments all at once, then you pretty much have to do it in the cloud. Or if you have, if you're doing reinforcement learning, like OpenAI does a lot of, massive experiments, or at least they used to, and a lot of them were CPU bound, not GPU bound. So that, then being in the cloud makes more sense. So let's see. Yeah, resource management is the idea that like, all right, if you have a few machines with GPUs, or maybe you have your machine, then you also have like a cloud environment. Or you have 5 developers and they each have a desktop machine, but they're not each running an experiment at the same time. They kind of stagger experiments. How do you actually get the resources from the multiple GPUs accessible through a single kind of job push? And so the oldest idea is spreadsheets. Don't recommend that. Scripts could actually be pretty good. It's just like simple script just asks the GPU if it's busy. And if it's not, then it puts a job on it. And if it is, then it waits. Slurm is the kind of industrialization of that. So it's really just a script that you say, OK, I'm trying to run a job. It needs 8 CPU cores and 2 GPUs. And I have a cluster of 16 GPUs and 86 CPUs. So like figure it out. And it gives you the right resources. Docker and Kubernetes is what these guys do. And the idea is that if you can package up your job as a Docker container, then you might have some jobs that only need CPUs, like you're extracting features. You might have some jobs that take those extracted features and run GPU training on them. So you have different kind of Docker images, and you have a disparate compute cluster. So how do you schedule like the different types of images onto the underlying hardware? Kubernetes is the answer to that. It's like able to take different Docker images and the underlying hardware and just kind of distribute things correctly. And the idea is great, but it has been pretty hard to actually get it working, and just a lot of boilerplate code. And if something breaks, like all of a sudden you're deep into the documentation trying to fix it. RiseML used to be a startup that promised to make it easy, and so it's basically something on top of Kubernetes that was specifically for machine learning. So you could just write a YAML file that said like, I'm trying to run these experiments. They need these resources, and then just hit RiseML train, and then have it figure it out using Kubernetes. Unfortunately, they shut down just a couple of months ago. So I think what I would advise to replace that with now is Cubeflow, which is something that's a project from Google that was started. So Kubernetes is also from Google, by the way. But Cubeflow is this idea of Kubernetes and Tensorflow in a nice kind of easy-to-use package. And it's supposedly based on Google's internal machine learning pipelines. But what it basically is it makes it easy for you to have a notebook that runs on Kubernetes. It supports TensorFlow, PyTorch, Chainer, and some other stuff. And then it also supports TensorRT and this thing called Selden for optimized production, which would be in the deployment lecture, so I'm not going to talk too much about it. But yeah, Cubeflow seems to be the way to do like machine learning on Kubernetes right now. But it also seems to be mostly about production and not actually training. So for distributed training, the idea is that you can use multiple GPUs not only to just run multiple experiments in parallel, but to actually train a single model on the multiple GPUs. Frameworks are getting better at doing it. The two things that you might hear is like data parallelism versus model parallelism. So data parallelism is essentially just partitioning your training data. And so it's the same model parameters on every GPU, but a different slice of the data going to the different GPUs. And then when you're doing backpropagation, at every layer, the different GPUs essentially just exchange parameters and average them out, and then continue down with their data. Model parallelism is way more complicated, and it's actually distributing the parameters onto different GPUs. So if you have like an 80-layer network, the first 40 layers might be on GPU 1, the second 40 layers might be on GPU 2. That's super complicated to code up, and the speed up tends to be not as good as data parallelism, so don't even worry about that. But data parallelism seems to be pretty good, and you get like pretty close to linear speed ups using modern frameworks like PyTorch and TensorFlow now. So TensorFlow distributed, Horovod is like Uber's answer to TensorFlow distributed, which is, I guess, also supports PyTorch now. But basically, it uses MPI, which is this thing from the 80s that is just a really good way to pass messages between different compute resources instead of like coding that stuff into TensorFlow, which is what TensorFlow distributed is. So I would recommend that. For experiment management, Lucas is going to talk about it right after me, so I'm not even going to touch it.
Can you go back to why TensorFlow distributed is different from TensorFlow?
Yeah, so TensorFlow distributed is, TensorFlow is this huge collection of things. It was huge at the start, and it keeps growing. And they're like trying to compress some things and make it more sane. But it's still a lot of different things that all have the name TensorFlow in it. TensorFlow distributed is the way to do distributed training for both data and model parallelism in TensorFlow. And the way they achieve that is with like TensorFlow code. So let's say you want to share parameters. If you're doing data parallel computation, the different GPUs have to share parameters between at every step in the backprop. So TensorFlow distributed is like code that TensorFlow has for doing that sharing, versus Horovod is kind of it's like on top of TensorFlow or PyTorch, and it uses MPI, which is a standard way to get information between GPUs or between CPUs or between computers. And so basically, it's like way more simple to implement than TensorFlow distributed.
So do you have to rewrite the code in TensorFlow distributed, or it can compile TensorFlow?
From my experience, TensorFlow distributed was not like a drop-in change to make. It usually requires re-architecting your TensorFlow code. I haven't personally experienced Horovod, but I heard it's a lot easier to implement. And so, and then these things are always getting better, I think, with every release as well. So it might be, TensorFlow distributed might be more of a drop-in change at this point than when I tried it. So yeah, experiment management. So hyperparameter optimization, when I had the slides, I suggested Talos and Hyperus. And there's a new one called Keras Tuner, which you have to sign up for early access. But this one's actually from Google, and I don't know, it looks really good. So I would recommend this one, Keras Tuner. So basically the idea here is like, if you want to, so here the learning rate is just going to be either 0.001 or 0.0005 or 0.0001. And that'll be part of like a grid of parameters, and Keras Tuner will sample randomly from it to get like the best things. And weights and biases as solution. And then for all-in-one, there's, that's kind of the idea is that there's a single system for everything, started from a hosted notebook to extracting features, to training the model, to potentially even deploying the trained model. Facebook Learner is like the internal solution. Michelangelo's internal solution at Uber. So Google is very confusing. They have the Cloud ML engine, which is kind of like that, except not for all steps. Then they also have something that they call TensorFlow Extended. And so at first it was just a paper. It was like a paper from 2017. And they said, we at Google found the best procedure for training machine learning models. It involves these steps: data ingestion, analysis, transformation, validation, then training, then model validation, then serving. But they didn't publish any code, even though they called it TensorFlow Extended. But recently they started publishing code. So now if you go to like I forget the website, but I think it's like, if you search TensorFlow Extended, now it's more of a thing. But I feel like it's still very confusing. But they made modules available for TensorFlow data validation, data transformations, model analysis, and then serving. And then in the middle is just like vanilla TensorFlow, which actually trains your model. So
Do you use something like TensorFlow Extended or Cubeflow?
no, No, I don't. Yeah, I haven't.
I'm saying like compared to Cubeflow and TensorFlow extended in the Cubeflow platform, what would be a better framework? Right? They're completely.
I think TensorFlow Extended is slightly different. It's just extending the range of what TensorFlow covers. So TensorFlow started as a way to like do essentially computational models. So that starts from formatted data and ends at output. And TensorFlow Extended is potentially starts from like raw data, so maybe like SQL rows or something, and then has code to transform that data into something that's trainable, and just like optimized code for all of that, and then doesn't stop at a trained model that's able to make predictions, but also potentially optimizes the model. So one optimization could be to like prune the number of connections in the model. So if like the different, from layer to layer, if there's a zero connection, you could potentially just remove it and not even go through a computational path. So I think TensorFlow Extended has that model validation optimization, so as a module. But Cubeflow is just saying, like, fine, you're trying to do all these things, but where are you actually trying to run them? So if you have some underlying hardware, and Kubernetes running on top of that hardware, then Cubeflow makes it possible to distribute the jobs you want onto that. And then the last thing I wanted to cover is MLflow, which is something from Databricks, which is the company behind Spark, Apache Spark. So they sell MLflow as an open source platform for the machine learning lifecycle. And what they try to do is they kind of have three things. They have a project format. So they say packaging format for reproducible runs on any platform. All it is like a YAML file that conforms to their specification. MLflow model is the idea that like if you follow the format, then the weights will be saved in such a way that you can use them with TensorFlow, or you can use them with Apache Spark, whatever they have, or just kind of a common way to save weights, right? Or save the artifacts that you need to actually make predictions. And then MLflow tracking is a user interface for recording the experiments that you run, which includes the code, the data, the config, and results, with like an open source interface to review that stuff. From what I've seen, it doesn't seem very good to me. Like people on Hacker News don't think it's very good. But people in the bootcamp mentioned it when I was talking about this stuff. So I thought I'd just mention it, MLflow. And then there's other stuff, Polyaxon. So there's way too many solutions here. There's Domino Data Lab, Polyaxon, all the Determine AI, Paperspace, Floyd, Neptune, all these things. I think the right thing and this is what I said in the lecture last time, I think the way to understand, to like stay sane, is to understand the parts that they're trying to do, and then just find your own solution to each one of those parts. So one of those parts is experiment management, and I think that's a very important part. And I would say probably the most important part. And really the only part that doesn't have a non-machine learning specific solution, right? Because people have been developing software and like packaging up deployment artifacts for decades. Like it's every time you deploy a website, you have to compile a whole bunch of like HTML and CSS code and upload it somewhere. Training a model is not so different. It's like you just run your training thing, you save your model, you upload it somewhere. But the one part of the machine learning lifecycle that doesn't exist in the rest of software development is the fact that you run multiple experiments and you have to keep track of them. So I think that's the most important part. Lucas is going to talk about that. Do you guys have any questions about the infrastructure stuff before we switch over? Yep.
With the hosted machines, hosted GPUs on-prem, how do you handle the changing requirements over the course of the project? So in the beginning, you might have one person prototyping, and then you might have a bunch of interns, and then you might want to do hyperparameter tuning or train like really large models.
You got to buy more machines.
It's not just, it's like the needs might change, like you might need more memory at some point versus more GPUs at another point. So
So I don't think in the project lifecycle the needs change, but I do think in a single training run, the computational needs do change. So for example, if you're training something on a large data set where you have like a bunch of, let's say, images, and you're trying to extract something from, like, let's say you're just trying to crop out a part of an image and then use that crop, and that's all you're going to use for training. So maybe you have like 1 million images, so you have 1 million crop operations that you got to do. Now those things are not GPU bound. Like you could just distribute them onto a bunch of CPUs and it would be just fine. But when you do those crops, at that point you want to send them into the GPU. So I think the problem that I faced is like you have a task that's CPU bound, but then the output of that task has to be data local to the GPU. So I don't have like a great solution to that. But I think that's where a cloud solution could be better, particularly like Google Cloud I think is very good because they allow you to like mix and match CPU. Like you can take any of their machines and then link up any of their GPUs to it. And so I think that could be very powerful. You could have like a machine with a bunch of CPUs and then do your pre-processing on that and then maybe link up GPUs to it at that point and only pay for GPUs at that point. So I'd say it is a problem, but it doesn't, I think as you hire more people, you just buy more machines and it tends to scale. Yeah.
Realistically, how you said in the lecture, I think 5 days a week, 10 hours a day or whatever.
Yeah, so I have like slides in here that just have some kind of back of the envelope calculations, which is basically like if you have a person working like a work week, like 40 hours, and then running experiments maybe overnight every now and then, how many months of that person's time, right, would a physical machine pay for itself in? And I think the answer was like 6 or something. So
my question is, in practice, how do you actually, are you guys able to keep the machines busy at that rate?
no, there's definitely, yeah, it's not busy all the time. It is spiking, but so one answer is if you get that data flywheel going, where essentially you like if you're able to train on fresh data every week, then every week you have a workload, and if you can get that down to a day, then that's even better. And if you have 7 models that you have in production, you train each one a week. Now you got a machine like working pretty much all the time. So that's actually what we do. But for a machine that's only for development, like no, experiments don't run all the time on it, right?
Sorry, after this question, you might have to
Okay.
save the rest for after
Sure.
this.
As you see the whole spectrum, I think what is really important is the whole deployment aspect, like containerization and everything, something like Cubeflow, and then the end-to-end process of raw data to the modeling, like something like Tensorflow extended, and for the whole experimentation setup, something like weights and passes. Like, is there like a good combination of all this to kind of set up this environment and
Yeah, so that's what these things promise. Like Neptune is a startup, Floyd is a startup that does this. Amazon SageMaker is an Amazon product that promises this. Determine AI is a startup that will do this stuff for you on-prem, like on your own machines. But
from your experience, do you suggest any good combination of these tools?
yeah, so what I suggest is just understanding the workflows. Like, okay, the notebook step is easy. That's just running a notebook. Distributing stuff onto GPUs is actually pretty easy. Like, depends on what you're trying to do, but like it's not that hard. Then you got to do experiment management. That's the part that I don't have a good solution for outside of things like weights and biases. And then you got to deploy it. I think it's perfectly fine to deploy on just CPU hardware, or CPU cloud instances. And we actually use Amazon Lambda. So yeah, my recommendation is not to buy into these all-in-one things, but to just kind of understand what they do and then just decide what you're going to do for each part. But the one part that I advise against coding yourself is the experiment management part, because that's just a lot of code that, yeah. Oh, well, I think that was the last question. Sorry. All right. Well, thank you. If you have any questions, Josh will tell you how to find me.